Most of the statistical inference procedures that we have examined so far rely on a statement such as the following. As the sample size goes to infinity, the statistics distribution approaches a chi-square or maybe a normal distribution. Of course, infinity is the one sample size that we can never have. So because of that, we don't have the exact probability distribution for the statistic. Rather, we are using an approximate distribution. Now, fortunately, there are many situations where a chi-square or a normal distribution work just fine. However, when the sample size can be small especially, these distributions sometimes don't work very well. Here's a nice quote from Ronald Fisher regarding this. Quote from a long time ago. Ronald Fisher is thought of as one of the fathers of the statistical science. And he said the following in his book. The traditional machinery of statistical processes is wholly unsuited to the needs of practical research. Not only does it take a cannon to shoot a sparrow, but it misses the sparrow. The elaborate mechanism built on the theory of infinitely large sample is not accurate enough for simple laboratory data. Only by systematically tackling small sample problems on their merits does it seem possible to apply accurate tests to practical data. What he's getting at is that there's a lot of high-level mathematics that are involved in showing that a chi-square distribution or a normal distribution serves as the actual distribution for a statistic when the sample size is infinity. But yet again, we can't have that particular sample size. And so that's what he's talking about in his statement there, that we have to develop alternative statistical inference procedures that are not necessarily based on the having a large sample. So the purpose of this section of the notes is then to develop inference procedures that look at the exact probability distribution of a statistic rather than using an approximate like a chi-square or normal distribution. And to do this, we need to introduce a new probability distribution called a hypergeometric distribution. For those of you who've had a mathematical statistics course, you most likely have seen this particular probability distribution before, but I expect a lot of people who are viewing this video have not. So here's a brief explanation of it, and I present it in the way that it is usually presented when it's first taught. Suppose we have an urn, and we have A, red balls in it, B, blue balls, so that in total we have N balls total, A plus B. Suppose K balls are drawn out at random from this urn without replacement. So, you maybe stick your hand in the urn, you're not looking at all the balls there, and you draw one out and you record, did I get a red or did I get a blue? You're going to do that K times. Let's let capital M be the number of red balls drawn out. This is actually going to be our random variable of interest. How many red balls do we get? M happens to have a hypergeometric distribution. The probability mass function is shown here. So the probability of having M red balls drawn out, where little m is a possible value, you could have 0 red balls, 1 red ball, all the way up to k red balls, since k balls total are drawn out. Here's the expression. A choose M, which represents how many ways can M red balls be chosen from the A total, red balls. B choose K minus M, so K minus M will be the number of blue balls. How many ways can you choose K minus M blue balls out of the B blue ones? All that's divided by then N choose K, which represents the number of ways that K balls can be drawn out at random from the N. Now note that A, N, B, and K are all fixed quantities. You would know those before actually conducting this, let's say, experiment. The only thing that's random is M, the number of red balls. Now it's important to realize that in this particular setup, each ball has an equal probability being drawn out of the urn, regardless of color. So that's why I said when we put our hand in there, we're not actually looking at the balls in there, we're just randomly grabbing one. Let's find some probabilities associated with this hypergeometric distribution. Suppose again, eight total balls. Four of them are red, four of them are blue, and we choose four, let's say, total out. So if I want to know the probability of choosing 3 red balls, I can plug in the corresponding values of n, a, b, and k into this expression. M ends up being 3. Do the math, you get 0.2286. And you could do this for other possible values of m. We could have up to 4 red balls drawn out. And here are the corresponding probabilities. So, is it reasonable then to observe, let's say, m greater than or equal to 3 red balls in this situation? Well, what would be that probability? Just add these probabilities together, and you would get about 0.24 or 0.25. So about 1/4 of the time, you will get 3 or more red balls out. This seems like a reasonable thing to happen, 1 out of every 4 times. How about, though, would it be reasonable to have 4 red balls? Well, in that particular case, the probability is only 0.0143. So maybe only 1 out of every 100 times would you actually get a red ball, and if you that you would get 4 red balls. And so if that were to happen to you, you would think, oh, that's kind of unusual to occur. I'm surprised by that. We're going to use that thinking very shortly when we do some statistical inference with the hypergeometric distribution. So how can I use the hypergeometric distribution then in R to find these probabilities? Here's really briefly how to do that. D hyper gives me my hypergeometric distribution. It finds probabilities, just like how the D binom function works before. And I'm going to create an M that has values of 0, 1, 2, 3, and 4 in it. And so when I use D hyper with that, with the 4 red, 4 blue, and then I'm choosing 4 balls in total out, I can use the D hyper function to go ahead and find probabilities with it. Now note that I didn't actually include the argument names. One could, in this particular case, I just assumed that I knew the order. I round to 4 decimal places, put into a variable named prob, print it off nicely with M, and here's my same probability distribution that we saw before. Okay. So the reason why we're talking about the hypergeometric distribution is because we're going to learn about something called Fisher's exact test. As you might expect, this is named after Ronald Fisher because he's the one who actually developed it. And basically, he used a hypergeometric distribution to figure out the probability of observing a particular contingency table. So, back from chapter 1, here's the contingency table that we looked at before. And I basically rewrote out this picking red and blue balls out of an urn in the context of a contingency table so we can see the relationships between the two. So, in this situation, we had N1 items in group 1, N2 items in group 2. This is like saying that I have A, red balls, B, blue balls. My response, either 1 or 2. Very often I'd say, this is a success, if I can spell it, and this is a failure. Okay? Now, for our situation with the urns, my response now is urn. I'm going to either draw out some balls or I'm going to leave some balls left in the urn itself. I'm going to draw out a total of K balls. So N minus K of them are left in the urn. Then I'm very interested in this here, M. M is the number of red balls that are drawn out of the urn. Now note that if I know what M is in the end, that means I know the total number of remaining red ones, A minus M. I also know how many of the balls that I drew out were blue, and thus also I know then the remaining number of blue balls that are in the urn. Now, a key thing to understand in this particular table, let me do some erasing, is that by how this experiment is done with the urn. These numbers are fixed. I know the number red, I know the number blue beforehand, and I've chosen how many balls and I'm choosing out of the urn. So those numbers are fixed as well. These are fixed quantities. The only random variable, if we think of this now as a random variable, is the m. Before, when we had binomial sampling, where each row represented the outcomes from a binomial distribution, n1 and n2 were the only fixed quantities. We wouldn't know what w plus and n minus w plus were prior to collecting the data. So we can see that there's some differences, but it's a small difference. And we can get around this small difference by using something that one would learn in a mathematical statistics course and say, okay, suppose I have a binomial distribution for row 1, a binomial distribution for row 2. These are independent, so what happens in row 1 doesn't have an effect what's happening on row 2. Given that information, if I were to, let's say, want to find the probability distribution for W1, if I think of that as a random variable, conditioned on how many total 1 responses there were, I would actually get a hypergeometric distribution. Not responsible for that in this class. There is an exercise in my book that talks about it, and in some mathematical statistics courses you would actually go through the derivation. Okay. I think we've already talked about this question here. How many cells in the 2x2 portion of the table would need to be known before all 4 values are known? You only need to know 1. That would be that W1, or equivalently the M. Now, for the first table, under independence, each element of groups 1 and 2 has the same probability of obtaining a 1 response. Same probability of success, let's say, under independence. We've learned that before. Now, in our particular situation with the hypergeometric, this is the same as saying each ball in the second table having the same probability being drawn out of the urn, regardless of color. That's what that would mean. It's going to be important as we go along here. So, we're next going to talk about this example called the lady tasting tea. This example deals with an experiment that might be the most famous experiment in all of statistics. It was done by Ronald Fisher one day a long time ago, and he was having tea with some colleagues. One of his colleagues was someone by the name of Muriel Bristol, and she's often referred to as the lady in terms of this lady tasting tea example. And anyway, she claimed that she could determine whether milk or tea was poured first into a cup. Now, I'm not a tea drinker, but I do know that people like to put milk with their tea or some kind of cream, let's say. And so, supposedly, she could determine if the milk was poured first in the cup or if the tea was poured first in the cup. And Fisher decided to design an experiment to help test whether or not she could actually do that. And here's the experiment. There were 8 cups set aside for the experiment. Tea was poured first into 4 of the cups. Milk was poured first in the remaining 4 cups. And the lady tasting the tea knew that 4 were tea poured first, 4 were milk. The lady, though, was blinded to which cup had milk or tea poured first. The lady tasted the cups of tea and provided a tea or milk response for all of them. Now, there's a great reenactment of this experiment that was on TV a few years ago on the TV show called Nova. This is a PBS TV show that often deals with science. And they had a whole episode on statistics. And one of the things that they focused on was the lady tasting tea experiment. So I'm going to show you a short clip from this particular TV show. And it's going to show the experiment, but it's also going to show some very other important things like how do we calculate p-values? And what does a p-value actually mean? So let me go ahead and open up the video and we'll watch this.
Surprisingly, it wasn't until the 1920s and 30s that a British scientist, Ronald A. Fisher, laid out guidelines for designing experiments, using statistics and probability as a way of judging results. As an example, he told the story of a lady who claimed to taste the difference between milk poured into her tea and tea poured into her milk. Fisher considered ways to test that. What if he presented her with just one cup to identify?
If she got it right one time, you'd probably, well, yeah, but she had a 50-50 chance just by guessing of getting it right. So you'd be pretty unconvinced that she has a skill.
Fisher proposed that a reasonable test of her ability would be 8 cups, 4 with milk into tea, 4 with tea into milk, each presented randomly. The lady then had to separate them back into the 2 groups. Why 8? Because that produced 70 possible combinations of the cups, but only 1 with them separated correctly. If she got it right, that wouldn't prove she had a special ability. But Fisher could conclude, if she was just guessing, it was an extremely unlikely result, a probability of just 1.4%. Thanks mainly to Fisher, that idea became enshrined in experimental science as the p-value, p for probability. If you assume your results were just due to chance, that what you were testing had no effect, what's the probability you would see those results or something even more rare?
If you assume that there's a process that is completely random and you find that it's pretty unlikely to get your data, then you might be suspicious that something is happening. You might conclude, in fact, that it's not a random process, that this is interesting to look at what else might be going on, and it passes some kind of sniff test.
Fisher also suggested a benchmark. Only experimental results where the p-value was under 0.05, a probability of less than 5%, were worth a second look. In other words, if you assume your results were just due to chance, you'd see them less than 1 time out of 20. Not very likely. He called those results statistically significant.
Statistically significant. Now, this is a terrible word. It could be quite insignificant. You could be detecting a very, very, very small effect, but it would be called, in the mathematical lingo, significant.
Okay, so that's a really good video that explains the experiment, how to calculate a p-value and what the p-value actually means. Not just in this particular problem, but just in general what p-values mean. A little bit of a side note. So I hope one day I can be one of those scientists that they interview for one of these TV shows that lend their expertise to help explain this kind of stuff to viewers. Maybe it will happen. Hopefully it will. Okay, let's move on here. Let's say that we have this hypothetical outcome of the experiment, where what we have for the columns are the lady's response. What we have for the rows is what is actually true. So if I have a 3 here, that means 3 times when milk was actually poured first, the lady guessed it right, that milk was there. 1 time, though, when milk was poured first, she incorrectly said tea. And then you can see the other results here as well. Remember, 4 milks, 4 teas are actually poured first. And the lady does know this, so it would make sense for her to always guess 4 for milk, 4 for tea. So we can see in these particular situations that the rows and the column totals are essentially fixed. The only random variable is this one right there, if not including this hypothetical situation. Now, if the lady could not actually differentiate which was added to the cup first, then her selection of the milk responses would be, in reality, be 4 random cups. And so if we can think of this then in terms of odds. So the odds of choosing milk would be the same as the odds of choosing milk when milk is actually poured first would be the same as the odds of choosing milk if tea was poured first. So the odds would be the same, and my OR would be 1. Thus, we would have independence. Now, under the independence, that's what the hypergeometric distribution provides us in terms of probabilities. So, in this particular case, and this is why I chose this, we have 8 cups. 4 are need to be decided as milk or tea to find out all the other components of that contingency table. And so here is the actual probability distribution that summarizes under independence what would happen. So if there was truly independence, that hypothetical outcome of m equal 3 has a probability of 0.2286 of occurring. Now here also I included the estimated odds ratios corresponding to my discussion about a minute ago. So in this particular case, the estimated odds ratio would be 9. How did I figure that? Well, 3 times 3 divided by 1 times 1, that's where I get 9. Now why do I have greater than 9 there? Well, in that particular case, we would have zeros in the denominator. If you replace the zeros with a very small number, you're going to get something much, much larger than 9. Okay, so this odds ratio calculations help you see the type of dependence that could occur in this kind of a table. Now, p-values are probabilities. An event is at least as extreme as what was observed. This is what you should learn in your introductory stat course. In fact, I always show this video too when I teach introductory statistics, even if we're not talking about Fisher's exact test, because it gives you a good understanding of what a p-value truly represents. Again, p-values are probabilities. An event is at least as extreme as what was observed under a null hypothesis. So under independence, here are the corresponding probability calculations. So at least as extreme then for us in this particular situation would result in the probability m is greater than or equal to 3 or 0.2429. So if this was the hypothetical outcome here, then it would not be unusual to observe 3 or more milks chosen. And in this particular case, relative to the lady tasting tea, we would say, okay, that's not unusual what occurred, that she got 3 right. So I can't really say then that she knows what she's talking about. So some questions here. I guess I've just talked about that one right there. Now, what would you say though if she got 4 right? Now you might be wondering, why am I not saying 8? Well, remember, we have these fixed quantities on the margins of the table. But let's say she got 4 right, so we have this. Would that be enough to say the lady knows what she's talking about? She can really differentiate between, if milk or tea are added first? Well, let's look at our probabilities. In that case, the probability of being at least this extreme ends up just being the probability m is equal to 4, and it's 0.0143. So there's only about a 1% chance that if independence was really true, she would get them all right. And so because of that, since it's so unlikely, then we would say, oh, I'm going to say that she does know what she's talking about, because it would be so unlikely for this to occur if she couldn't tell the difference. So what does an odds ratio greater than 1 here mean? Well, let's take a look at this. Go back to the table. Let me get my eraser out again. Well, let's interpret this odds ratio here. The estimated odds of concluding that milk was poured first are 9 times as large for when milk is actually poured first than when tea is poured first. So that odds ratio is telling us, hey, maybe something, at least in this sample, we're going in the right direction in terms of the lady being able to tell that indeed milk or tea was poured first. Then, my estimated odds ratio was greater than 9, then there's even more going in the right direction. But if this was 1, think about what this means in terms of this contingency table. In that particular case, oops, let me get my eraser out again. In that particular case, if I had m equal 2, I would have 2 here, 2 here, and 2 here. Think about this. The odds of concluding that milk was poured first when it truly was would be exactly the same as if tea was poured first. So, you really can't tell the difference. Think about it, though, in this situation, too. Suppose I had this. So she got them all completely wrong. She totally guessed the opposite. In that particular case, the odds ratio, estimated odds ratio, would be 0. And so, obviously, that's not what we want to have happen if we want this lady to succeed and be able to tell the difference. So then if I wanted to, I could set up then formal hypotheses, such as this. I want to test this. Oops. Let me get my eraser. Sorry about that. The null hypothesis is OR is less than or equal to 1. What that says, if OR was equal to 1, we have independence. If it's less than 1, that means she's doing the opposite of what is actually true. But if OR is greater than 1, then that says, okay, she knows what she's doing. She can tell the difference. And so those are the hypotheses I want to test. And that's what Fisher's exact test does here. Now, the lady ended up actually did getting all 4 right. So we can say then the p-value for this was 0.0143. So in how we normally would interpret a p-value in this situation, we have marginal evidence that indeed the lady can tell the difference between if milk or tea was poured first. Let's look at how the calculations are done in R. I can then enter the data, the actual data, into an array, into the array function, put the array function results into c.table. Here's my contingency table. And simply, if Fisher was actually running the analysis in R, he would use his function, fisher.test. And for the x argument, we put in the contingency table. There's an argument called alternative, which corresponds to, notice my HA is greater than, and so that's why I put a greater. Here are the results. My p-value is 0.01429, which is exactly the same as what we got from using the hypergeometric distribution. Now, in other situations, not this one, in other situations, you might want to do a two-sided hypothesis test, meaning you have this. And if one were to do that, the p-value ends up being 0.02857. Okay, so how is this two-sided hypothesis test calculated? Well, it's simply found by adding all probabilities that are less than or equal to the probability corresponding to what was observed. So if we go back to our table, in this particular table, we have symmetry here, so we would add this probability to this probability, and that would be the p-value for a two-tail test, or two-sided test. Now note that unfortunately, all exact inference procedures, and this is an exact inference procedure because we're using the exact probability, the hypergeometric distribution that governs what's going on here. All exact inference procedures are or tend to be conservative for hypothesis testing. What that means, just to review, that means that you will reject less often if the null hypothesis is true. You will reject less often than the stated type 1 error rate. So if alpha was 0.05, you would expect, let's say, the actual or the true type 1 error rate to be less than or equal to 0.05. Now, if you had a larger 2x2 table, you can also use Fisher's exact tests. In this particular case, the hypergeometric distribution is simply extended to include like a 3x3 table, a 3x4 table, and so on. One could do that. If you're interested in the exact details, take a look at my corresponding book. For those larger tables, we'll just rely on the Fisher.test function to do the calculation for us.